today we're going to start talking about the structure of the atom. And like I told you yesterday, that this unit tends to be pretty abstract and it tends to be tough. This is probably one of the hardest units that we'll do this year, but it will also be the unit that we keep coming back to. It's going to explain so much of everything else that we're going to learn about. It truly is worth the effort. So we're going to start way back in 400 BC. We're going to do a little history lesson here. Not because I really enjoy it. Actually, a little bit before 400 BC. Not because I enjoy it, but because it's necessary to know where we've been so we can see how far we've come. We're going to start with Aristotle. Have you guys all heard of Aristotle? A philosopher, a know-it-all, a person that people really believed. He is responsible for the fact that for a long, long time, people believed we had 4 elements. Earth, wind, fire, which by the way is a great music group, and air. So he believed matter was composed of a combination of these 4 elements. And I mean, we obviously know that that's not true today. But for example, if we would crack open a human, there'd be stuff that would be runny like water. So obviously humans are made of water. And there would be stuff, I mean, it's warm inside of us, so there's some fire in there. And the bones, if we can grind those up, they kind of look like dust, so there's probably some earth in there. And we obviously breathe in and out, so we've got air in us too. So we are a combination of these 4 elements in a unique kind of amount for each. So, you know, the combination, the percentages of air, earth, water, and fire that would be contained in me would be different than would be contained in each of you. And that's really how they explain the world. If we crack open a rock, we don't see any water, right? There's nothing that flows in there unless it's a really hot rock. But if it's just a plain old rock that we would find outside, it's earth. Probably some air in there. You can see some little pockets where there would be something and there's nothing there, so it's got to have air in it. And they really just made up their world based on that information. People believed him for like 2,000 years. And because he was a teacher, it was pretty prolific. Like it was just around for a long time. He was a teacher, he was influential, people believed him, and he was obviously wrong. So that was a problem. In about 400 BC, another Greek man by the name of Democritus, he did what we call a thought experiment. And he really just thought about it, and he said, okay, well, if I cut, if I take a piece of iron and I cut it in half, now I have 2 pieces of iron, but it's still iron, both of them are still iron. Well, if I take one of those and I cut it in half again, now I have 2 more pieces and it's still iron. And he just kept doing this over and over and over in his head, and he thought, at some point, I'm going to get down to a small piece of iron that when I cut it open, it's not going to be iron anymore. And he called that thing that still retained the properties of iron, the Greek word is atomos, which is where the word atom comes from. But he called it atomos means indivisible. So he said there's some small piece of this that when we're going to get it, it's really tiny. We're going to get down to that smallest piece and it's not going to be divisible anymore and still be that substance. So Democritus is really the first person that is credited with coming up with this idea of an atom. And for him, this is what it looked like. It was just this round thing that had properties of the overall substance itself. And you couldn't break this open there because if you did, it wasn't that substance anymore. People thought he was nuts. Like, clearly, there's no way that's possible. Because what really made Aristotle uncomfortable was the fact that that means there's empty space. And Aristotle just didn't believe that. So, I mean, he created all kinds of things to fill that empty space. The ether was one of them, very popular. Even still today, we have people who believe that there's an ether everywhere that fills the empty space. Then there's no scientific evidence to support that. So it wasn't until the 1700s that we have actual experimental evidence that supports what Democritus thought of. John Dalton was an Englishman, and he was doing gas experiments, and he was also a teacher. And what he did with his results was he was able to determine that atoms exist, all right? And for him, the atom looked like this, very much like Democritus's atom. It's actually the same picture. John Dalton was very meticulous in his experimental work, and based on his data, he was able to say that there is a smallest piece of matter, and that matter is called an atom. He kind of was a throwback to Democritus, like, haha, he was right. But this is the first experimental evidence that we have. John Dalton also put together an atomic theory. The atomic theory that it was the first attempt at an atomic theory. And, let's see, this was in 1803, all right? So Democritus in 400 BC, and then all the way to 1803, this is the first time that we have evidence of what's going on. So about 2,200 years-ish. John Dalton's atomic theory, this is what his experimental evidence supports. The first part is that matter is composed of small particles called atoms. All matter can be broken down into simpler pieces, and we're going to call those simple pieces atoms. Okay, it's pretty clear, pretty straightforward. The next part that he put on here is that atoms are indestructible and indivisible. And remember I said that the word Democritus used for an atom was atomos, which means indivisible. So John Dalton, again, supports this idea that the atom is small, it makes up all matter, and it can't be broken down. So indestructible and indivisible. We can't break it into smaller pieces. The next part, and there are 6 of them, by the way. The next part is that atoms of a given element are identical. So in John Dalton's experiments, one of the things that he noticed was that if he had an oxygen atom form, it was the same as the oxygen atom over here, which was the same as the oxygen atom over there. Same thing for any of the elements. If we have an element and we look at the atoms, they're all identical to each other. This was what his experimental evidence supported. And, I mean, again, all of the material, if we just keep cutting it into smaller and smaller pieces, you're going to have the same stuff every time we make that division. So all the atoms are going to be identical to each other. The next part is that atoms of a specific element are different than those of a different element. And that kind of makes sense, but they laid it out here for people just in case. If I have an atom of iron and I have an atom of carbon, those two things are going to be very different from each other. But all atoms of iron will be the same, all atoms of carbon will be the same. It's just when we compare different elements, they're different. Next. Different elements combine in small whole number ratios to form compounds. This is basically telling us that when a compound forms, you're not going to have half an oxygen combined with 7 hydrogen. It's got to be the whole thing. We can't have pieces and parts of atoms, and that kind of makes sense if you look at number 2, which says atoms are indestructible and indivisible. We can't have half an atom of something. But when we form compounds, the elements are going to combine the same way every time, and it's going to be a small whole number ratio. And we're gonna come back to this a couple of times as we learn about chemistry, but this was part of his original atomic theory.
Well, this feels like something important to remember.
I'll tell you specifically what you have to remember. And then the last part is that in a chemical reaction, atoms are separated, combined, and rearranged. So in order to see change, we're going to see that things actually break apart. They kind of move around a little bit, and then they recombine. That's what a chemical reaction is.
But again, all of these pieces are supported by his experimental evidence. First time we have experimental evidence to support the idea that atoms exist. So do we have questions about that? We're good? We just need to write it down? Okay, so let's go ahead and go on, because we're not done with all the people. Right? So, in 1803, John Dalton published his atomic theory. It is not the current atomic theory. It's not we have a modern atomic theory, and we're not gonna, John Dalton's atomic theory is important, but we're not gonna talk about what important aspects there are about it until we talk about the modern atomic theory, because it's really the comparison of the two. So that brings us to J.J. Thomson. J.J. Thomson was, he's a scientist that he was working at Cambridge University in England. And I don't know if you know anything about Cambridge University, but it's like a big university. It's prestigious. It's been around for a really long time. J.J. Thomson was working with photo tubes, and they're just sealed glass tubes that contain gases, and he could change the gas that was inside of the tubes, and he would pass electricity through them. So you'd have an anode on one end and a cathode on the other. That's just electrical, like, things. You'd have, so the electricity could pass through the gas. And what he noticed is that he would get a beam to show up anytime he passed the electricity through the gas. Today, I think about it as a fluorescent light bulb, right? If you've ever looked at a fluorescent light bulb, there's not really anything in it except for gas. And when we plug it in, we've got electricity going through the light bulb. It goes through one end, passes through the gas to the other end, and it lights up. It's similar, very similar to what he was doing. And one day he was in the lab and he kind of flipped everything on, and there just happened to be some magnets in the area, and what he noticed was that the magnets affected the way that beam moved. So, he's a typical scientist, lab rat kind of guy. So he started investigating. It always starts out like with playing with it. So, okay, so I have this thing here. What if I do this with the magnet? Well, okay, what if I do this with the magnet? What if I flip the magnet over and I put it on top? And he was just kind of like playing around with it, investigating it a little bit, and accidentally discovered the electron. I mean, one of those serendipitous discoveries. He just accidentally discovered the electron. And that's why he's super important. He published his work in 1896. So 1803, John Dalton publishes his atomic theory. And anytime any new information like that is published, then all these scientists are like, I want to either verify what he did, I really hope that I can come up with some kind of experiment that's going to disprove what he did, because then that gets you a bigger name. And everybody wants to know now, what are these atoms, how do they behave, what can we know about them? So he discovers the electron, and he says, well, you know what? That model that John Dalton came up with, like the marble kind of thing, well, that's clearly not right, because we have these electrons. So J.J. Thomson in 1896 publishes what he thinks of as the model of the atom, and this is what he thinks it looks like, where you have this spherical thing, and the pink stuff is like this positively charged stuff, goo, I don't know. The electron then are located, spread evenly throughout that. Because we know that electrons are negatively charged, protons are positively charged. We also know that matter is neutral, because if it wasn't, if protons and electrons didn't equal each other, every time we touch something, we get shocked. And obviously you can go around and touch things and you don't get shocked. So they knew that matter was neutral. He knew there had to be something positive that was balancing out the negative charges. This is referred to as the plum pudding model, because in England, plum pudding is like a big deal. In American, we've Americanized it, so in America we call it the chocolate chip cookie model, right? Where the chocolate chips are the electrons, and the cookie itself would be represented by the positive stuff there. So once this was discovered, then there was a whole rush of people that were just investigating the atom, and like, what else can we find out about it? What else can we figure out about its behavior? So that introduces Robert Millikan. Now, Robert Millikan is an American physicist, and the really kind of neat thing about Robert Millikan is that he's the only American. Oh no, I think James Chadwick is American. He's the first American that we see kind of pop up into our scientific history. Anybody want to guess why? Owen?
Because this is soon after America finally started to get going.
Yeah, I mean, America is a baby of a nation compared to some other places in the world. And they were worried about just, like surviving, not being eaten by bears, having enough food to survive. So, I mean, he's the first real physicist that we see, American physicist that we see that pops up in our radar. Robert Millikan, very intelligent man. I'm not sure I'd want to be married to him though. I mean, so I had to do his experiment when I was in college. I did it in my general physics class, actually. And so what it was he created this thing. It almost looks like a set of binoculars. And it looks into, I guess it'd be more like a microscope. And it looks into a box that has oil in it. Has water in it. And you spray these really tiny droplets of oil into the water. And then there are these electric plates in there that you put electricity through, and he balanced these oil droplets in the center of these two plates. So like he spends hours at these microscope lenses trying to do this and adjust the dial on the electricity that's going through these plates, and he collects all this data. I can't imagine that he was real pleasant after a long day of doing that, right? But what he determined was the mass to charge ratio of an electron. Okay, now J.J. Thomson discovered the electron. Didn't know anything about it other than that it was negatively charged. What Robert Millikan did was he was able to calculate the mass of the proton and from this mass to charge ratio. And he noticed that the charge was in whole numbers. So he theorized that the charge of the electron has to be, I'm not going to even give you the number because that's not important at this point, but he was able to calculate what the charge of the electron was. And that way we could know that there would be 1 electron on that oil droplet or 7 electrons on that oil droplet just based on his data. He proved that they're particles. So let's go back to John Dalton's atomic theory for a moment. What was that third one? Okay, I lied. The second one? Atoms are indestructible and indivisible. Well, with Robert Millikan and J.J. Thomson's work, we proved that electrons are smaller than atoms. That electrons they are a component of an atom, and that they're smaller than atoms, and that atoms are not indivisible. Okay, so all this work is going on. Some of this stuff is going on all around the same time. Ernest Rutherford also a physicist. He's a professor at Cambridge University during this time when he's doing his work. And he's actually got groups of students, grad students, that are doing this research, and he puts his name on all their papers, so he gets credit for it as well. Now, Ernest Rutherford's grad students, his groups, they actually discovered two things. Okay, discovered two things. The first was the nucleus. The nucleus was the first thing to be discovered outside, well, the electrons were the first thing to be discovered. The nucleus was the next to be discovered. And this was in 1909, I think, 1906, somewhere right around in that time, so right at the turn of the century. 1896, we have the discovery of the electron. Robert Millikan is doing this work after the electron is discovered. Ernest Rutherford discovers the nucleus of the atom right at the turn of the century. So I actually want to show this one to you because this one is really important. He's using the gold foil experiment. And this is really important that you understand what the gold foil experiment is.
In
1910.
1910, co-workers were studying the angles at which alpha particles were scattered.
Okay, let's pause that. Let me put the sound through the projector so you can actually hear it.
It's called the foil.
Gold foil.
Are there any notes on this, or do we take them from here?
This is the only thing that I have about it.
The gold foil?
Yeah, gold foil. So let's start this over.
Do you want us to take notes on it?
You should be able to explain it, but if you wanna like watch it, and then if you need the link, I'll be happy to post the link. This is something you can find in a lot of places on the internet, so if you don't understand it now, you can always look up information about it later.
We did it in our freshman year. We did it.
You did your freshman year,
I just
yeah.
don't remember. But
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So that was just short and sweet. It really just gives you an overview of what the experiment was. Now, again, this is right at the turn of the century. So I want you to think about like what kind of technology they had at the time. They would have usually a lead box. The lead box would have an opening. It'd have just a small hole. And through that hole, the alpha particles would go. So you'd have something inside of the box that it would decay, it would break down. The nucleus is giving off these particles of energy and these particles of matter. So these particles are shooting out of that small opening, and they're directed at a piece of gold foil. Now the gold foil itself was just a couple of atoms thick. It wasn't very thick at all. They hammered it into really fine sheets, and it was suspended inside like a little frame, and they had detectors all the way around it. Now they didn't expect to get the results they got. They didn't expect it at all. And it totally revolutionized the atom, the structure of the atom. But based on those results, Ernest Rutherford's group determined that the structure of the atom couldn't possibly be what J.J. Thomson predicted. Ernest Rutherford's group said it's got to look something like this. You've got a really tiny, dense, massive nucleus, positively charged nucleus in the center, because these alpha particles are coming out of this lead box really fast, and if they come and they hit that nucleus dead on, they start to accelerate. They slow down and then change directions and start heading backwards. So you gotta have something that's really, really small and really, really positive in order to cause that type of acceleration, that change in direction, based on these really tiny particles that are moving fast anyway. And then you have all the electrons that are outside of the nucleus. And this was referred to as the planetary model, right? You can kind of see the nucleus is represented by like the sun, and then the electrons are outside of the nucleus like the planets. It'd be really bad if we were in the sun. Today it's kind of hot, but it's fine. So this was his model of the atom. Now, a few years later, his group went on to discover the proton. So at this point, they only knew about the nucleus. But eventually, they were able to determine that there are protons in the nucleus. That's the positively charged thing. That made a lot of sense because we have these negatively charged electrons, and you gotta have something that balances it out. So, Ernest Rutherford's group, they discovered the nucleus first, and then they discovered the proton. That brings us to James Chadwick. In 1932, James Chadwick is doing experiments with radioactive materials, and he discovered the neutron. Now, Ernest Rutherford's group knew after they discovered the proton that something was still in the nucleus because the masses didn't make sense. But they couldn't figure out what was in there. They couldn't find a way to detect it because they were able to detect charged things. They were not able to detect the neutron because it's neutral. So in 1932, some of the experiments that James Chadwick did with radioactive materials, he was able to determine that there are neutral particles in the nucleus as well. And that accounted for the mass that was missing in Rutherford's model. So we have all of these pieces put together. Here's the model after Chadwick discovered the neutron. We have all these pieces sort of coming together to create this picture of an atom. As we have these discoveries, we can refine our model. And it gets more detailed, and we know more, and we can look closer at it. Now, I will tell you today, this is not the correct model of the atom. I will also tell you that after all of this information was discovered, and in recent years, we've been able to determine that protons and neutrons are made up of even smaller particles called quarks. And I'm sure you heard a few years ago they discovered the Higgs boson, and there's just constantly these tiny fundamental particles that we're looking for. We're predicting that certain particles exist, and then there's just the search for these particles. But as we learn more, we can refine our model, and we can sort of figure out, we're trying to figure out exactly what it looks like. So, here's what we knew after all of this work. Here's what we know. We know that there are protons at this time, after all of these discoveries have been made. We knew there were protons, electrons, and neutrons in the atom. We knew that protons and neutrons were located in the nucleus, which was the center of the atom. And that nucleus is really small, and it's spherical-ish, and it's really dense, which means those protons and neutrons are packed in there tightly. Okay? They are close together, they're smashed into that small space, which creates another problem, because protons repel each other. But we knew that. We knew that this was the case. We knew that the electrons were not in the nucleus, right? They're somewhere outside of the nucleus. Not real sure if there's any organization to that or if they're just kind of like out there. They knew that the atom was mostly empty space and that the majority of the mass for the atom is located in the nucleus. Approximately 99.97% of the atom's mass comes from the nucleus. The electrons make up roughly 0.03% of the mass. They're really tiny. And they knew that matter was neutral. So those are the things that they knew. And it seems like a lot. Seems like a lot. But there are a lot of things they don't know as well. They don't know why the nucleus stays together. Right? There's all those positive charges in there, and positive charges repel each other. They didn't know why that was happening. They didn't know why the electrons didn't fly into the nucleus. They didn't know, it made people very uncomfortable that there's empty space in the atom. Like, what's in the empty space? The answer is nothing, but that made them very uncomfortable. They also wanted to know if there was some structure to the electrons, right? Because they didn't know that at the time, they just knew that the electrons were there. So this is what they knew, a lot of things they didn't know. That brings us to isotopes. Now, we're gonna just briefly talk about isotopes. If you are a senior, we did this when you were a freshman. If you are a junior, we have never done this before. So we're gonna just go through this briefly, and we're gonna come back to it later on, but we do need to discuss it. What time is this period over? 05, okay. So this will probably be the last thing that we discuss as isotopes today. So isotopes, the definition is that they're atoms of an element with different numbers of neutrons. Now remember, part of John Dalton's atomic theory is that all atoms of an element are identical. Isotopes tell us that they're not identical. There are two parts of John Dalton's atomic theory that are no longer true. So these atoms of elements with different numbers of neutrons, they are identical to each other. And it makes sense that John Dalton didn't have a clue because, you know, again, he was working at a time where they didn't have real sophisticated equipment. I mean, they had some sophisticated equipment, but it was all homemade and it was for a specific purpose. He wasn't able to look at the atoms, he wasn't able to determine their mass. He was looking at them on a larger scale. They are chemically identical to each other. So they behave the same way when we talk about reactivity. They behave the same way when we look at pretty much any property of them. All of them are the same color as all the others. The isotopes were difficult for him to, or for anybody to identify, but they do have a slightly different mass than each other. So one atom of carbon has a slightly different mass than a different isotope of carbon. And it's not even a huge difference, it's just a really tiny difference. In order to identify the difference between them, the different number of neutrons, we have to use a mass number. So I'm going to tell you the mass number is the number of protons plus the number of neutrons. I'll say that one more time. The mass number is the number of protons plus the number of neutrons in the nucleus. So it's how many particles are in the nucleus. Sometimes the particles in the nucleus are referred to as nucleons. That represents all the particles in the nucleus. But it's the total number of protons and neutrons in an atom. And different isotopes have different mass numbers. They have the same number of protons, but they have different mass numbers. So anything that we find in nature, let's say that I find a hunk of carbon in nature. All of them, all of those carbon atoms have 6 protons. All of them have 6 protons because they're carbon atoms. That's how we identify them. So they all have 6 protons, but there's a mixture of isotopes in that one sample. Some of them might have 6 neutrons, some of them might have 7 neutrons, some of them might have 8 neutrons. It just depends. These mixtures are constant, and we use them, we know what their abundance is. So for example, in middle school, did you guys talk about carbon dating?
Oh, right, for carbon what?
Carbon dating, radiometric dating. So we use carbon dating to determine the age of fossils. It's because we know how much carbon-14 there is and how much carbon-12 there is, that the amount of each of those is constant. So by comparing how much carbon-12 or carbon-14 is in that fossil to how much is present just in the regular atmosphere, we can determine its age. So that's what this means. We're going to come back to this, and we're going to do some calculations about this later on, but I wanted to briefly talk about this because it helps us understand where they, like some of the discoveries that they made with atoms. So just briefly, and this is the last, well maybe, we'll see. So this represents the nucleus of a carbon-12 atom. The protons, let's see, the protons are red. All right, so 1, 2, 3, 4, 5, 6. We have 6 protons. That's a carbon atom. And then in this particular isotope, we have 1, 2, 3, 4, 5, 6 blue ones. Those are our neutrons. This is a carbon-12 atom. This 12 is our mass number, and that is the total number of particles that are in the nucleus of the atom. 98.9% of all carbon on the planet is carbon-12. This nucleus has 1, 2, 3, 4, 5, 6 red ones. That means it's carbon. It's got 6 protons. And it's got 1, 2, 3, 4, 5, 6, 7 blue ones. That's neutrons. It's got 7 neutrons. So this is carbon-13. This again is our mass number, total number of particles in our nucleus. And only 1.1% of all carbon on the planet is carbon-13. This last nucleus is, again, is for a carbon atom. We have 1, 2, 3, 4, 5, 6 red ones. Those are our carbon, or those are our protons. 6 protons means it's carbon. But this one has 1, 2, 3, 4, 5, 6, 7, 8 blue ones. Those blue ones are our neutrons. It has 8 neutrons and 6 protons. That means there are 14 particles in the nucleus. This is carbon-14. Carbon-14, the abundance of it in our just natural, like everyday life, 0 or less than 0.1%. Really, really tiny amount. So by comparing how much carbon is in a fossil or a rock to how much carbon we have naturally, tells us something about its age. And if we are here and we can get through the end of the year, we have a unit on radioactivity, and we will talk a lot more about this. Okay? But obviously the atoms of an element are not all identical, because these are all carbon atoms, but they are not identical to each other. But look at, I mean, we didn't even know the neutron existed until 1932. So there's no way that John Dalton would have been able to predict this. But the amount of stuff that he was able to discover based on his experimental data is pretty impressive. I know you can, I know you're impressed. Like, you're just speechless, you're so impressed, you're impressed. Okay, last slide. All right, so here's what we knew about the electrons. And what we were confused about. And when I say we, I mean the scientific community. Not me literally, I'm not that old. Pretty old, but not that old. So we have 3 subatomic particles. The arrangement is still unknown. Of the electrons, right? Well, and of the neutrons and protons too, because they know that the protons and neutrons are located in the nucleus, but sometimes protons and neutrons can't get out of the nucleus. We don't understand that. The electrons, we have no idea like exactly where they are and what governs their behavior. We have Rutherford's model. So the nucleus at the center is positively charged. The electron's not in the center. But the connection between what the structure looks like and the reactivity of the elements, that connection is still very fuzzy. So that's, a problem. And when scientists see questions like this, then what they want to do is they want to investigate it. They want to figure it out. They're natural problem solvers. They're natural puzzle doers. So these guys, they're, like being able to say, well, we don't know what the connection is between where the electrons are and what their reactivity is. That gives them a spot to do all of their research and try and figure it out. Why are the electrons not pulled into the nucleus? Because we know positives and negatives, they are attracted to each other. The positives are in the nucleus, the negatives are not in the nucleus. How is it that they don't fall into each other? So that's confusing. And then some elements emit visible light when they're burned. So when we burn these things, and let me show you a picture of that. Or a video. I thought it was just a picture.
Please note that this video was made solely for research and demonstrational purposes. Do not attempt to repeat the experiments shown in this video. Hello everyone. Today I will show you one interesting experiment, which is called the fire one that you can find in our kitchen, is cooking salt. It will
Okay, so the actual, like, words are not important. But, what's happening here is he's gonna light these on fire in a moment, and let me actually just go to that. What you're gonna see, well, I'm just gonna show you. I'm not gonna tell you what you're gonna see, you're just gonna see it. We could definitely get different colors. Now, I don't know what they were doing during this time period when all of these things were being discovered, and this was at the end of the 1800s and the beginning of the 1900s, when a lot of this was being discovered. I don't know what they were doing, where they were just burning things. I don't know if like labs went up in flames all the time and you saw all these wonderful colors. I have no idea. But this was something that they absolutely knew happened. And you can see that second one in there, it's kind of like purple. You get some really brilliant colors. This is the science behind fireworks, right? All the different colors that you see in the sky. Obviously, we're not going to burn lead nitrate. We don't really want to introduce lead into anybody's diet or lungs. But, you know, and it's hard to see in the night sky, but this was all stuff that they knew. There were a lot of things that they didn't know. And they couldn't make the connections between them. And you guys know how big I am on connections. But I'm going to point out that this introduces light into this discussion. Now tomorrow, we are going to start our discussion with light. Those of you that took physical science, we did a little bit of this. But we are going to really talk about light and the properties of light and a lot of the things that were going on at the time. Because all these different pieces are going to come together and create a modern model of our atom that we now know or believe is the best model for the atom. Okay? You guys have any questions? Okay. The expectation is that you are going to interact with me at some point. I know all of you, you don't need to be shy. It's Maddie's fault, so I don't know. Okay, so the more you interact with me, the better you'll learn. And the more entertaining it is for me.
How was your day?
My day? Hectic. You know, science. Oh yeah, this is still.